All right, we're going to talk through the conclusion for the harmonic motion lab that we did earlier this week, and it will be due Monday. So first, in your intro, we're going to be starting us off with like an explanation of what simple harmonic motion even is, and why did our device show simple harmonic motion. So just notice that should be lab. But anyway, basically what I'm looking for is that you have a definition of periodic motion or simple harmonic motion, and then explain why mass on a spring meets that requirement. The next thing that I'm looking for is that we define these four terms: equilibrium, period, amplitude, and restoring force. It may make sense to just knock them all out in the intro, but you could also kind of pepper them in when you're talking about them naturally throughout your paper. So if it makes more sense to do them later, that's fine, but I'm at least looking for a definition of all four of those words. The next thing, we're going to address both research questions and your hypothesis to those. The first research question was about whether amplitude makes an impact on period. And hopefully from your findings, we did, some of the groups we did it in class, some actually took data, but the whole point was that that the period had nothing to do, there was no interaction with amplitude, meaning I could stretch that thing further and further and further. It doesn't matter how far I stretched that box down, the timing that would take to go back and forth, up, down, would be the same. Now, besides just saying that it doesn't make an impact or that it ended up being the same, I'd like you to go into why that works out. And so what we're looking for there is that you go into the fact that if you pull it down further, it is true that the velocity is larger, but the displacement it has to go through is larger. So, pulling the spring down to a larger amplitude would make your velocity go up, and your displacement will also go up. But since velocity is displacement over time, if velocity goes up and displacement goes up, so if these two are going up, that time value is staying fixed. If we just bring it back a small displacement, kind of go back to our thing, just a really small displacement, you have a very small velocity and a very small delta x, but again, the timing would still be the same because time would end up equaling delta x over velocity. And so because this ratio keeps working out to be the same, it'll keep working out to be the same time. So that's really all I'm looking for in the conclusion, the conclusion for that first research question about amplitude and period, is that it doesn't make an impact because when you stretch it further, yes, it is going faster in velocity, but it's also displacing more distance, and therefore that work keeps working itself out to get to the same time value. Now, the second research question was the mass research question. That was what we took more data on. So that is going to have a little bit, more to it as far as what you have to explain about the experiment. But again, you'd address our research question was, how does period get influenced by mass? Then you can address your hypothesis and say, I thought it was going to be a direct relationship, but it turned out to be a square root relationship. So mentioning that as a square root relationship for that second research question, that's going to be big for identifying the type of relationship. All right, the next thing, then we plotted data and we graphed it, and what we should have seen was that when we graphed period versus mass, we ended up with this kind of flopped over square root graph. So the relationship was square root, and in symbols we would just say period is proportional to the square root of mass. Once we did that, we linearized our graph, so we made a new graph of period versus the square root of mass, and got a straight line. And the units then of our slope would work out to be seconds divided by square root of kilograms. And that's not a terribly meaningful unit to us really, but that's just what the units come out to be with our graph. So as far as which graphs I want printed, You don't need to include a graph from the first research question, the amplitude graph. We don't need that. I would like the linearized graph, though, this period versus square root of mass. You can choose to print out this one also, the very first one we did. So if you print that separately, that's fine. Or if you even just sketch that in your journal first, and just have a sketch of this, just kind of an overview of like how it came out, just like how I did here, that it came out with the side opening parabola. And then, but this is the main one that I want printed, is this linearized version. So if you choose to print both, fine. If you print just the one, then make sure that you include just a sketch of the original graph in your next, in your journal. All right, the math functions that come out of this. So your particular math model from your graph, again, coming off the linear line like you had for period and square root of mass, would say that period is equal to, let's just say your slope came out to be 7. 7 seconds per square root of kilograms times square root of mass plus whatever y-intercept you would happen to have. So that's your math model. Remember, it's specific to your exact data, your math model is. Then the larger formula, the general formula for simple harmonic motion of a mass on a spring, was what we gave you in large group, which just says the period for a spring is equal to 2 pi times the square root of mass over the spring constant k. So I'm looking for both of these. I want, your specific math model in there, and then I also want the general formula to be in your final conclusion. All right, an extra thing we're going to have you do with your slope is to kind of pick it apart and find the spring constant in there. So if you remember, you had we did this right at the end of class on Thursday, but with your period versus square root of mass graph, you had this relationship, and your particular math model would say that period equals your slope value times the square root of mass. Again, if I gave it a number like 7, then the number 7 would be in there. Well, what's in this, actually, what's left over in this is just coming from the larger formula from a spring that we just talked about, T equals 2 pi square root of m over k. So everything that's not in your math model here, okay, anything that's in this formula that's not in this setup would be what's embedded within your slope. So that means that 2 pi times the square root of 1 over k, kind of do it like that, that is all included in your slope calculation. So because of that, then we're going to solve for that, and just to show you how that math would work out, let's say my slope was 7. Well, that means slope of 7 would equal 2 pi times the square root of 1 over k. I'm solving for k, so I'm going to divide by 2 pi on each side, and then that'll cross out there, and then I'm going to square each side. Okay, and that'll get rid of the radical. And then I'm going to invert each side, basically take 1 divided by each fraction, so 1 divided by this whole deal, and that will get me my k value. So I apologize, that's a little messy, but it's just kind of all 3 algebra steps kind of stacked up at once. So just working through systematically, I divided by 2 pi to get that to the other side. I squared both sides to get rid of the radical, and then I inverted both sides to get k just sitting by itself. So we want you to report your slope value, and that would have units of newtons per meter. And remember, that's just a reference of how strong your spring is. All right, next thing, we're looking for some other examples of simple harmonic motion, or if you can even think of some that would represent this lab. So, things that come to mind, I'm thinking bungee jumping, pretty much anything that bounces up and down and repeats that pattern. But you can also get into things like pendulums, swinging back and forth. You can get into systems that just vibrate up and down, You can think of water waves that just kind of oscillate back and forth. Circular motion, something spinning around in a circle. There's lots of different examples of simple harmonic motion. So, come up with a few to share, and then that will take care of the examples. The thing that you're going to do is talk about your sources of error. So, sources of error, we're looking for very specific things, and there's a lot that could lead to error in this. When I was just looking through data, I saw quite a few people that just had a number that was way off the mark. And, all the other data was falling in line, then you had one that was just completely off. Well, there's a lot of things that could explain that. We could have, timing issues with you divided by 4 oscillations when you actually recorded 5, something like as simple as that, where you intended to record 5 oscillations, but you actually only stopped the stopwatch after 4 oscillations. I saw that happen a few times. There was other things where some groups were timing it right when they started. They would let go and they'd hit the stopwatch. Well, it hadn't really reached a natural rhythm yet, and so they may have been skewed for their timing on that first hit. Some other just the stopwatch error, the reaction time error is a huge one. So, we can't be exact in watching for that bottom of that arc or the top of the arc, wherever that thing was supposed to get back to. And so a lot of times what happens is we anticipate when it's going to get there. So we kind of stop it early or we start it early, and that plays into this. So besides those kind of timing things, and again, when you mention those, don't just say timing errors. Be specific. I mentioned several specific examples of what could happen with timing. But I want you to then also think about the energy loss. So we did not have perfect conservation of elastic potential energy within the system because of friction buildup. So lost a lot of it to friction. When that spring starts shaking up and down, it kind of gets smaller, 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 and smaller. The amplitude dies out. Now you can still see the period. We know that amplitude doesn't affect period, but it gets harder and harder to see that, and that could have an impact on our overall value. The other thing that kind of works into this is the fact that we did it vertically, and when you do vertical spring displacements like we did here, you have gravity kind of helping it out with momentum on the way down, and then kind of working against it on the way up. So it's not a fair fight as far as like how it oscillates back and forth. Whereas if you do it horizontally and look at that going back and forth, the gravity acting on it is the same throughout the whole scenario. So these examples are more realistic, or I guess better closely suited to simple harmonic motion. And so some of our error could have been just the fact that we had to do it vertically just to get our data. So those are the things I'm looking for. And again, those will be due Monday. And get those typed up or written up and into your journals. We want those graphs printed by Monday as well. Enjoy your snow day and go sledding or do something fun. I'll see you Monday.